Let's jump right into this explainer, where we are going to completely demystify the OSI model. Now, if you've ever tried to study computer networking, you already know this model can feel like a really dense, overly academic puzzle that is notoriously frustrating for beginners. But today, we're going to fix that. We're transforming it from a dry textbook concept into a totally practical toolkit for understanding exactly how your data moves and, honestly, more importantly, how to fix networks when they inevitably break.
Here's our roadmap for today. We'll start with the universal networking language, then trace a web request's downward journey, unpack packets, frames, and bits, dive into TCP, UDP, and network protocols, apply it all with bottom-up network troubleshooting, and wrap up with why the model still matters. Basically, we're doing a top-down look at how data is packaged and finishing with a bottom-up approach to fixing it.
All right, kicking things off with part 1, the universal networking language.
So to get started, you have to realize the OSI model isn't just theory. It's the universal language of networking. It slices insanely complex global systems into 7 manageable layers. And to memorize those layers, IT pros have used a classic, kinda silly mnemonic device for decades. Please do not throw sausage pizza away. It sounds a bit ridiculous for sure, but it is an incredibly easy way to remember the layers from bottom to top. Or actually, if you prefer working top-down, you could go with all people seems to need data processing.
So what's actually in this 7-layer cake? Working down from the user to the literal cable, we have layer 7, application, then layer 6, presentation, layer 5, session, layer 4, transport, layer 3, network, layer 2, data link, and finally layer 1, physical. Every single piece of data you ever send or receive has to travel through this exact foundation, no exceptions.
Let's move right along to section 2, a web request's downward journey. Let's make this real. Imagine you just type cisco.com into your browser. Your data starts at the very top, at the application layer, where your browser queries a DNS server, basically the internet's phone book, to find an IP address. Then it drops to the presentation layer. Here, data gets encoded into ASCII text or JPEGs, encrypted for secure HTTPS, and compressed. Next, it hits the session layer, which opens dedicated connections just to make sure the data for this specific web request doesn't somehow bleed into your other open browser tabs. All of this organizing happens before the data gets anywhere near the actual hardware.
Which brings us to section 3, packets, frames, and bits.
Now, as that perfectly prepped data moves down the stack, the lingo actually changes. Down at layer 4, the data becomes a segment. This is where it gets handed off from your computer's software to the network's functions using specific port numbers. Think of ports like apartment numbers in a massive high-rise. If your computer is the building, port 80 ensures the segment gets delivered exactly to the web server application rather than getting lost in an email client.
Dropping down to layer 3, we box that segment up into a packet. And this is the spot where we slap on the source IP address of your workstation and the destination IP address of the server. An IP address is basically a zip code on a piece of mail. It provides the crucial routing info to get your packet to the right general neighborhood across the sprawling internet.
Next up, layer 2. Here, the packet transforms into a frame and gets stamped with physical MAC addresses. If the IP address is the zip code, the MAC address is the literal name written on the individual mailbox. Your local network cards and switches rely entirely on MAC addresses to know exactly which physical machine gets the data on the local network.
And finally, we hit rock bottom, layer 1. The frame gets blasted out over a wire, fiber optic cable, or Wi-Fi radio wave as a raw bit. All that high-level software, the complex encryption, the routing data, it all boils down to literal pulses of electricity or radio waves, just digital zeros and ones making the physical jump to the very next device.
All right, section 4, TCP, UDP, and network protocols.
Before we get into fixing broken networks, consider the 2 heavyweights of the transport layer. First, you've got Transmission Control Protocol, or TCP. It's like certified armored mail delivery. It constantly verifies every piece of the message to guarantee it arrives without corruption. On the flip side, you have User Datagram Protocol, or UDP. UDP sends data without any checks at all. It's literally like throwing a paper airplane and just hoping it lands. But because of that, it is incredibly fast. That's exactly why we use TCP for web browsing where accuracy matters, and UDP for live video streaming where speed beats perfect delivery every time.
Think of this next concept as your master cheat sheet. It is so incredibly helpful to map these real-world protocols directly to the OSI layers. Right up at layer 7, you've got familiar stuff like HTTP and DNS.
Just below at layer 6, TLS is handling encryption. Down at layer 4, there are those TCP and UDP protocols we just talked about. At layer 3, you have your crucial IPv4 and IPv6 routing. And down at layer 2, Ethernet and MAC addresses are doing the heavy lifting for local delivery. Keeping this map in your head, it is absolutely the key to our next topic.
Which brings us to Section 5, Bottom-Up Network Troubleshooting.
Okay, let's get into the real-world stuff. Picture this scenario. Someone frantically tells you the network is completely down. You walk over, take a look, and notice there is no link light on their switchboard. Where do you even begin? Well, troubleshooting works best when you stop guessing and just start at the bottom. Because if the foundation is broken, absolutely nothing above it is going to work. That missing link light, boom. It instantly isolates the fault to layer 1, the physical layer. You know exactly what to do. Check the hardware, look for chewed up or unplugged cables, check for bent pins, verify the power. Seeing this as a physical fault saves you from wasting an hour messing with IP settings when the literal cable is just unplugged.
But what if the local hardware is totally fine? Let's say the user has a solid link light, and they can print to the office printer just fine, but they completely fail to reach remote internet sites. What layer is failing now?
That is a textbook Layer 3 network fault. Since local traffic works, we already know layers 1 and 2 are perfectly fine. The issue is specifically how the data is routing outside the building. So you'd investigate the IP addressing, verify the default gateway, or check for a duplicate IP conflict somewhere on the network.
And now for the trickiest scenario of all. What if your network pings succeed to the server, but the actual website application still times out for the user? What in the world is broken here?
Well, a successful ping means layers 1 through 3 are working flawlessly. You got to look higher up. It could be a layer 4 issue like a blocked TCP firewall port, maybe a layer 5 issue like a dropped VPN session. It could be a layer 6 fault like a mismatched TLS security cert, or just a layer 7 application issue like a busted DNS lookup. This proves a really important point. Raw network connectivity is not always the same thing as application health.
Wrapping things up with Section 6, Why the Model Still Matters.
Look, mastering these 7 layers, it doesn't just help you fix computers. It fundamentally changes how you see the digital world around you. By adopting this troubleshooter's mindset, you don't just see a magical black box when you open your laptop anymore. You see a logical, beautifully layered machine just waiting to be understood. So the next time your internet randomly drops, I want you to ask yourself, which layer is failing? Are you ready to look deeper?